Yes, welcome to another presentation on various bias configuration of transistors, right? So far we have covered the various biasing configuration of transistors, right? If you go through our previous presentations, there you can find the various configurations which we have covered, like fixed bias configuration, and the second one is collector to base bias configuration, as well as the third one is self bias configuration or emitter bias configuration, and then also called as universal bias configuration, or otherwise also called as voltage divider bias configuration. So predominantly we have three types of transistor biasing configurations. In today's presentation, I would like to give a simple and very simple brief example on fixed bias configuration, right? So this is very much important in your academic examination point of view, or even your gate examination point of view, and even your UPSC IAS examination point of view also, right? This is very important model normally you can expect on your fixed bias configuration, right? So this is the given problem basically. This is a given fixed bias circuit. This is the given fixed bias circuit because the entire theory I have not given, but directly I am giving in this presentation is that the given problem is this. The given circuit diagram is like this. So it is a common emitter amplifier where emitter is grounded. This is emitter basically, and this is your base terminal, and obviously it is your collector terminal. Collector resistor, base resistors are given, and both are connected to supply voltage which is 12 volts, and the input is here. Actually at base we have given input actually through the coupling capacitor 10 microfarad. Similarly the output is taken at collector point through this coupling capacitor, again 10 microfarad. You are taking out the output. Now the question is, find, this is the question, find the quiescent values of base current and then collector current. The quiescent values of IB and IC, where Q stands for the quiescent or operating points, actually those are also called as the quiescent point. So quiescent base current and quiescent collector current, and that is the A bit. And coming to the second bit, VCEQ, quiescent value of the voltage, I mean quiescent value of the voltage between collector to emitter terminal, means you have to find out VCE here, VCEQ between here. This is what VCEQ means. And your IB is nothing but through this terminal, means through this RB, your base current flows like this. The current whichever flows through this RB or base resistor is nothing but IB, and you can call it as IBQ also. And your IC is nothing but the current which flows through this RC, that is nothing but your IC, also called as ICQ. Nothing wrong in that. You can call it ICQ, or you can call this IB as IBQ, nothing wrong. So you are asking the to find out what is the value of IB, what is the value of IC, what is the value of VCE in overall. So how to find out these quiescent values of base current, collector current, and then the voltage between collector to emitter terminal. It is very simple. It is very simple, right? So I will erase here and I will give you the solution of this. Okay. So if you see the solution, it is very simple actually. There is nothing difficult. So if you see the solution part, let us see, always remember that I already very clearly explained in the last previous three biasing configurations that to find out the stability factor, yes, what we have did actually, we have applied the KVL, Kirchhoff voltage law, at input side of the transistor, is it not? So the same way whatever we did in our previous presentations, for different biasing configuration, the same thing, exactly the same thing we have to do here. We have to perform same operation here also. So by applying KVL at the input side or input loop of the transistor. What is the input loop? Start from this plus VCC, right? Start from plus VCC, coming through this RB, and then just up to come up, so you can reach up to the emitter point. Means that you have to apply the KVL at this input loop actually. Remember that the collector, the coupling capacitors. So these two capacitors at the input side as well as the output side. This is the coupling capacitor at input side. This is the coupling capacitor normally at output side. Remember that we are discussing the DC analysis part. While discussing the DC analysis part, obviously the coupling capacitors are ignored. There is no purpose of these capacitors while discussing under DC analysis. In fact, if you consider the same circuit in AC analysis, then these capacitors will come into the picture. That we will see in the next subsequent presentations. And even I can explain you that I will explain you the DC, the low frequency analysis as well as the high frequency analysis of the transistor. There are various methods are there to analyze the circuit in at low frequency configuration as well as the high frequency. So this is what the low frequency actually. The DC biasing is nothing but. So this is called as, all the biasing techniques belongs to the DC analysis, also called as low frequency analysis. In low frequency analysis, the capacitor, whatever the coupling capacitors we are using now, CC, they will not taken into consideration. Therefore, don't worry about these capacitors. Don't consider even, right? Let us focus on the resistor part, and properly we have to apply the KVL. Thereby, you have to get the required parameter, right? So by applying KVL at the input side, what is the input side? So as I have indicated in the circuit, it starts from plus VCC through this RB, and then here if you see between this base to emitter, we have the internal voltage, that is nothing but VBE. Base to emitter voltage will be there internally. This is plus and then minus. Clear? The internal voltage will be there, right? Therefore, if you apply the KVL at the input side, what will be the equation? By applying KVL, so you have to write the same. By applying, what is that? By applying KVL at the input side, at the input side of the transistor, then what you will get, tell me what will be the expression? It is VCC. I am writing here. VCC is equal to, tell me, RB into, so the input supply voltage is equal to whatever the potential appears across this RB. What is the voltage across RB? It is nothing but RB into IB. This much is the voltage actually. RB into IB plus what will be there? VBE, base to emitter voltage. VB. This is the equation. By applying your KVL at input side, you will get this expression. Am I clear? So VCC is equal to IB into RB. So base current into the resistance RB plus VBE. And from this particular expression, you have, so plus VCC, that is 12 volts. What is the VBE? Remember that the base to emitter voltage, right? Assume that the transistor is of silicon. Most of the time, if nothing is given in the given problem, you will assume that it is of silicon transistor. So for silicon transistor, your VBE, base to emitter voltage, is 0.7 volts. Therefore, from this, actually, if you write the expression for IB is equal to, it is VCC minus VBE by what is that? RB. This IB normally called as your quiescent value of base current. Then what is your VCC? It is 12 volts minus VBE 0.7 volts. Remember that it is 0.7. That is the standard value for silicon transistor. And what is your RB? 240 kilo. 240 kilo. Kilo means it is 10 power 3. Therefore, if you substitute with your calculator, and obviously you will get something 0.0 0.047, it is something milliamps, right? So your IBQ value is 0.047 into milliamps. That is whatever, I mean, your IB, quiescent value. And here in this given problem, the beta value also given here. Remember that the beta is given. Beta is equal to something, it is given like that 50. Beta of the transistor. What is beta? Beta, what is the beta? Beta is the current gain. It is the current gain. What is the current gain? Output current by input current. What is the output current? IC. Input current is IB. Therefore, your beta is nothing but IC by IB. Remember that. This is the relation. IC is the collector current, IB is the base current. Therefore, if you take the ratio IC by IB, that is what beta. Therefore, so your IBQ. So from this relation, what can be written? This implies, so IC is equal to, and also you can treat it as ICQ, that is beta times IBQ, right? Is it not? What is beta? It is 50. What is IBQ? 0.047 milliamps. And you can substitute from your calculator. Normally you will get something 2.35. Approximate values I am giving actually milliamps, maybe. So these approximate values, almost all nearer, right? So this is what ICQ, right? So the first parameter is IBQ. Already you got this value, and so if you substitute that IB in this relation, means beta is equal to IC by IB, IC is equal to beta IB into B. So you can treat it as IBQ and ICQ. From there you can get this value ICQ as like this. Then definitely this is A bit actually. Now coming to the B bit, VCEQ. So for the B bit, what shall be done? What we can do for the second bit? So for the second bit, so apply the KVL at the output loop of the transistor. This is by applying KVL at the input loop actually. Now you can apply KVL at the output loop. Clear? You can apply KVL at the output. What is output loop? This part, plus VCC through RC plus VCEQ. So you can write the same by applying, KVL at the output loop or at the output side of the transistor. Whatever you can write, no problem. Output side of the transistor, right? What you will get? Again it is same. VCC is equal to here IC into RC. Now you can write IC into RC. Then plus VCE. Is it not? Plus VCE. That's it. So this VCE you can call it as VCEQ. No problem. And from this, what can be written? I have to find out the relation for or the value of VCEQ. Therefore, VCEQ is equal to what you will get? It is VCC minus IC into RC. You know everything. IC is nothing but ICQ only. In fact, VCC is the same. Your VCC is equal to 12 volts. What is ICQ? It is 2.35. This IC is nothing but ICQ itself. 2.35 milliamps. Okay. What is your RC? 2.2 kilo. So this kilo and milli cancelled out, because milli is 10 power minus 3, kilo is 10 power plus 3, both will be cancelled out, and you can get your VCQ almost all. How much? Almost all you will get something. It is about 6.83 volts. 6.83 volts you will get actually. What is this? VCQ. That's it. See how simple it is. So the only common sense is that you have to apply the KVL, Kirchhoff voltage law, at the input side of the transistor, similarly at the output side of the transistor properly. That's it. Then by substituting in the relevant expressions, and you will get the desired equations. Clear? I hope that you understood well this simple example on fixed bias. Okay, with this we will finish off this presentation here, and then we will continue in the next presentations with some more examples on this fixed bias as well as the remaining two biases also, collector to base bias as well as the emitter bias or voltage divider bias, that we will cover in the next presentation, right? So with this we will finish off today's presentation, and thank you very much for watching this video, and then do not forget to share this information with your friends, and especially in your friend circle. Okay, and also request you all that if any observations on comments or the things or the topics which actually you feel were missing something, you can give your feedback so that it will be taken up in the next subsequent presentation, and we'll try to cover those topics also in the subsequent presentations. Till then, have a beautiful day.